Let's discuss part 5 of AC bridges. We are starting off with measurement of capacitance. We shall be discussing two bridges under this heading, de-Sauty's bridge and sharing bridge. Ideally, we assume that capacitor is not power dissipating in nature, okay? But practically, this dielectric acts as a resistance, okay? So this causes some power consumption, and the dissipation factor of the capacitor is given by inverse of a quality factor, okay? This is your required phasor diagram over here with regards to capacitor. Now we are discussing de-Sauty's bridge. This is your required circuit diagram. Here we are comparing this unknown capacitor with this known capacitor, okay? And we are finding this in terms of your known capacitor. Once you balance this bridge, you can easily put this formula into use and calculate your unknown capacitance. You can also calculate your unknown dissipation factor with the help of a known dissipation factor, okay? And your dissipation factor has this following formula. This method, however, has a disadvantage that it has low accuracy, okay? This is the required phasor diagram of your de-Sauty's bridge, okay? Now we shall be discussing sharing bridge. This is your required circuit diagram over here, okay? Same thing, we are calculating the unknown capacitor with the help of a known capacitor here as well. At balanced condition, you use these particular formulae. You calculate your unknown C1, okay? This is unknown C1, and you can calculate your R1 also, R1. Then we have this, and this delta is also known as dielectric loss. Now what we are doing is, this is your required phasor diagram of your sharing bridge. Now we shall be discussing about measuring relative permittivity. This is the bridge, okay, we are concerned with. What we are doing here is that we are calculating the relative permittivity of the dielectric medium of a capacitance, okay? So let's get to the terminologies we shall be dealing with. Here CT is the total capacitance with dielectric, and C0 is the capacitance without dielectric. CD is the capacitance with dielectric only, okay? And area of the electrodes, D is the gap between the specimen and the electrode, T is the thickness of the specimen, and this is the reduction in separation between two measurements, okay? So first we are calculating total capacitance with dielectric with this formula, okay? What we are doing here is, first we are balancing the bridge to calculate the value of this capacitance, okay, along with the dielectric, okay? And then what we are doing is, we are removing the dielectric medium, and then we are calculating it, okay? So you get this without dielectric. Now you get the capacitance with dielectric and without dielectric, so you know how much capacitance is due to the dielectric. So what we are doing is, we are removing the dielectric and separating the plates to such a distance between them that it behaves like that, what do we say, that dielectric, okay? We are creating that dielectric effect with the help of air, okay? You increase the gap, it is bound to behave like that, okay? So you are creating the same reading, and this is how we are calculating. Now this is your required thickness. Here you see thickness of the specimen, your dielectric thickness is given by T, okay? This is all we are doing. Now these are the formulae you will be dealing with while solving numericals. This will be all the more clear, but the funda here is, you first take your capacitance and balance this bridge, and you find out this relative permittivity due to dielectric, okay? Then you remove the dielectric and then calculate the relative permittivity, okay? Then you will find some difference that is due to the dielectric medium. So this is how we are doing in this particular method over here. Now the advantages are, finding unknown this and this is pretty easy, okay? You have formulae for everything. Unknown capacitance can be found out using this method. Your angle, which angle, your dielectric loss angle, can be also calculated, okay? Your errors can also be calculated, okay, if you are facing errors regarding the measurement of capacitance or the relative permittivity, okay? The error is also easy to calculate. Now we have earth metal screen provided to reduce interarm capacitance between the low arm of the bridge. Now this interarm capacitance is also producing some errors, so what we do, we put the earth metal screen, okay? So this capacitance is grounded, okay? Then we have Wagner earthing device, okay? This is to remove all the extra stray capacitance to the ground. Okay, what we are doing here, this is your required circuit diagram, and this is your Wagner earthing device over here. What we do over here, first this is your switch, you shift it to A. Okay, you are adjusting it to A, then you adjust the value of R1 so that this shows a null deflection over here. First you connect the switch to A terminal, then vary this resistance so that this detector shows null deflection. Then what you are doing, you remove the switch and then connect it to B terminal, then vary this RW in such a way that this capacitance over here gets discharged. Okay, first you what do we say, first you put this switch on A terminal, vary R1, okay, so that your capacitance gets charged. Now you disconnect from A and you connect it to B. Okay, now you vary this RW over here so that this capacitance over here gets discharged. Okay, this is what we are doing. The stray capacitance gets grounded. Okay, here you see the extra capacitance is going to ground. So this is all for part 5.